Um, Hello everyone. My name is Shammi, and I'm the TU of this course, Sobolev spaces and partial differential equations. And welcome to the week 2 of this course. I am a research scholar at Institute IIT Delhi, and um, so this week in the lecture notes, in the lecture videos. Uh, so taught us basically about the distributions and some more properties of distributions and some distribution derivatives and how can we see convergence of sequence in in the space of distributions. And then we have what we saw actually convolution of functions and eventually we saw that convolution of functions can be lifted to the convolution of distributions, but that was just introduced, and more theory will be developed in the upcoming weeks. So our main focus today will be on like some more questions based on the distributions and the PD involving distribution, so that we have an idea that if we have a PD, like how can we get a distribution and solution out of it, and we'll see convergence in the space of distributions, how the convergence happens, and some example based on that. So that will be our target for today's video. We will do some question on these topics. So without further ado, let's start our discussion on these topics. So first of all, we would like to solve again first questions, and for initial questions will be based on on the PD. We would like to find the distributions that satisfy that particular PD. Well, in fact, not a PD. I would more sense I would say like I would say it's like a equation involving a distribution. So it's more like that, but can be constructed in a way. But it's like it's one of the ways to solve the one of the ways to reach that particular goal. So let me write the question. Find the general solution of the following equations for T in distributions. And we're doing this for A, comma B in R, with A is not equal to B. So the very first example we are considering is x minus A T equals delta B. And delta is our Dirac delta. Okay, so we have to find all such distributions so that they satisfy this particular equation. So how we basically go about solving these type of questions? We try to first see this like an equation. So it's like uh, some distribution T when multiplied with x minus A is actually giving me a Dirac delta at B. So the idea is to find the first is to first find the homogeneous solution and then try to find some particular solution out of that homogeneous solution. So first solve homogeneous equation. So what is the homogeneous equation? X minus a t equal to 0. First of all, let us try to solve this homogeneous equation because we want to find a general solution. So any particular solution. So how do we solve basically this particular homogeneous equation? So we have seen that in our earlier lecture that we have this thing. We saw like last time we did one question that this x minus a times t is 0 in distributional sense if and only if I have my t is of but particular form some constant times Dirac delta at a or some constant positive. So this we did in last tutorial. So so the solution of this homogeneous is nothing but some constant multiple of Dirac delta. Next, what we'd like to see, we'd like to see next if t solves x minus a t equal to delta b, then I will let t will be a form of t plus th plus tp, where th is what th is basically the solution of the homogeneous portion. Th is basically th is again a distribution which solves x minus a t equal to 0 and tp is some particular solution of x minus a t equal to delta b. So what this will imply? This will imply that this will imply what this will imply. This will imply that T is a solution of so what this basically implies if I have this T is if this of particular form Ts plus Th plus Tp, then it satisfies then it satisfy basically the equation. Next, we will show that if any other t which satisfy this particular equation, then it will have this of this form. So that will basically characterize the solutions of the general solution of the equation x minus a t times delta b. Now, if t equal to th plus tp solves the equation, then where tp is the tp is some particular some particular solution, then I know that since this is satisfied, we have this is equal to delta B. What this implies? This is imply that x minus a th plus tp equal to delta B. But as we know that TP satisfies this equation, then x minus a is nothing but delta B only. So this implies that TH has to be the solution of the corresponding homogeneous equation. So it basically characterizes the general solution. So what now we do basically we we now the only task, so now we know the general solution, but we have to find some particular solution, and once we have the particular solution, we know we already have the homogeneous solution. So once we have the particular solution, we will be able to basically um, get the general solution of the corresponding equation we have. So construction of TP. So we just need to find some particular solution. So how do we go about it? We know that x minus a t is equal to delta b. So so if we see that t ultimately is ultimately ending up being a Dirac delta function, and that too at x equal to b. So the guess we would go with that t has to be of some form Dirac delta at b, but we don't know the con. It will be a constant multiple of that, but we don't know exactly the constant. So initially we take c, if where c is some constant. And let us now try to put this t in this. So x minus a t also is nothing at, basically we have to check at any phi. So for phi in dr, we're considering this. So this is nothing but x minus a c delta b at phi, and this is nothing but c delta b at x minus a times phi. So that's how you define the distribution, multiplication distribution via C infinity function. And now this is nothing but C, and this is nothing but B minus A, and this is nothing but phi at. So this is B actually. And what do we basically want? We want this thing equal to basically Dirac delta at B. So we want x minus a t phi equal to delta B phi, which is nothing but phi at B only. So this what this gives us, let's see, we have to take upon have to be B minus A only. We have to take C equal to 1 over B minus A only. So the particular solution we are getting is nothing but thus TP will be of this part of this form. This will be of this form Dirac delta at B whole divided by B minus A. And of course, we are taking A is not equal to B. So what this implies thus The general solution is given by T is equal to TH plus TP. And what is TH? TH is nothing but some constant times drag delta. So we have written that. So TH is actually from the previous position constant times delta A. So this is nothing but C times delta A plus 1 upon V minus A times delta B. So this is the form any general solution of the equation. So you see the idea of solving this particular equation is nothing but the same idea when we solve this non-homogeneous ordinary differential equations, and the idea we basically do, we take the general solution is nothing but the general solution of a homogeneous equation plus some particular solution of our given ODE. So the same idea we used here to basically construct the general solution of our distribution equation, I would say. So, so that's how we basically go with solving this type of equations. Now we'll see more examples of this distribution equations, and to have a more better understanding or understanding in solving these type of equations. So the part B, so earlier was the part A. So part B was the part 2. Nothing but x minus A, x minus B, t equal to 0. So this is the second problem which we like to solve. So we need again all the distributions which satisfy this particular equation. So it's already an homogeneous equation, and so to solve this, first of all, we observe that so this is more like a, a combination of what we have done in earlier lecture and this last equation. So so to solve this, we see that if we take x minus b times t, put to some s, then this is nothing but x minus a s equal to 0. And we have seen the solution of this particular equation. So, but we know that x minus as is 0 if and only if s is of this platform some constant multiple times the Dirac delta at a. Then so this basically what we end up solving is now that's what we have, as we know that s was nothing but x minus p times t is some constant multiple of Dirac delta at a. But what is this? This is nothing but the first type of equation we had. So this was x minus a t equal to delta b, and the solution was this particular thing. So this was t. So now the roles of a and b are reversed here, and not only that, we have extra constant there, which wasn't there. So let me write that constant by c1. So the solution now from part 1, the general solution solution T is given by. So since instead of delta, first we know that T was given by TH plus TP, and the homogeneous solution is going to be the same as something C2 times some delta, and since we have x minus a times T here, so homogeneous solutions, it will be some C2 times delta B, and then the particular solution will be of the form. We need to again normalize the C1 constant. Earlier, that constant was C1, but now we have a multiple of C1, so we just have to multiply with C1 with the particular solution, and the general solution we can write in the form that the particular solution was given by delta B times B minus A. So just to have more constant, then we have just have to multiply the solution by C1 only. This will be C1 times delta A and then whole divided by A minus B. So if we like to just compare the solution, particular solution with the earlier one, we end up getting the particular solution to be of this form. And this will actually give me the general solution of this distribution. And again, you guys can see that since there are two parameters A and B, we are ending up with getting two constants C1 and C2. So actually, those two are in multiplication with my distribution. That way it's coming. Earlier it was on the right hand side, and so that's why we are not getting any constant there. But here we are getting two constants because there is a multiplication with t only. So continuing our discussion, let's have more examples. So the next example which I'd like to consider is the 1 plus x square, 1 minus x square t equal to 0. So now again we'd like to find the all distributions t which satisfy um, um, this particular equation. So and then we see that this x minus a, x plus a, this are ending up giving a Dirac deltas because these things have actually have a we are basically these are C infinity functions which has zeros. So basically to eliminate the effect of zeros, we have to multiplication by their reciprocals. And since they have zeros, so when I multiply by reciprocals, these reciprocals will actually give me the singularities at the zeros, and these singularities will eventually give me that the singularity can be basically captured by the Dirac deltas because Dirac deltas is something which actually in some way we can see shoots at that particular point, shoots infinity at that particular point. So it's the same idea basically. So if we don't have any zeros, we can see that we can have a division or a proper multiplication by the reciprocal of that function. So so to solve this, what we try to do, we know that this 1 plus x square is never 0 for all x in R. Then what can I do basically? This implies that I can 1 upon 1 plus x square will belong to C infinity R. That's a basically distribution function. Thus, what this implies, I can multiply this thing by both sides. Ultimately, what do we have here? I can multiply by a C infinity function. And this will basically implies 1 minus x squared times t is nothing but 0. So now you reduce our equation to a smaller equation, and again we can write this thing as x plus 1 and x minus 1 times t equal to 0 with like some appropriate multiplication of minus 1. So now this is what this is nothing of this is nothing but x minus minus 1 and x minus 1 t equal to 0. So this is something like x minus a times x minus b times t equal to 0, and that's was our second part. So, and we know the solution was given by this particular form. So ultimately we can write the general solution. This the general solution is given by is given by nothing but some constant times the Dirac delta at 1 plus another constant time Dirac delta at minus 1. So ultimately that particular factor we are taking for the constant that is not required, because ultimately we are ending up multiplying with another arbitrary constant, and we can that particular constant can be absorbed into this general constant. So ultimately the solution will be of this form only. So let us try to generalize uh, this this equation. Ultimately, we are solving an equation with like a polynomial multiplied by a distribution equal to 0. So that is the sort of sort of equations we are solving. So let's have the more generalized version out of it and try to solve that. So px t equal to 0. So now we have a polynomial here, and what we're taking where px is nothing but x minus a1, x minus a2, and x minus an, with the condition with a1 is less than a2, which is, and further a2 is less than a3, and so on and so forth. So this is the equation, the final equation we are saying. This is the equation which I would like to, which I would like, we would like to see how to solve this particular type of equation. So the idea will remain the same only. So how do we end up solving this? So what we try to do, so to write the solution. So So what I'm trying to write is what I will write this. First of all, I need to solve px t equal to 0. So let f1 is nothing but the remaining vector apart from the first vector, x minus a2, x minus an t. Then what do we have to solve? We have to solve basically x minus a1 s equal to 0, right? And as we have seen, and this is 0 if and only if. What do we have? F s of what form? S1 is of what form? Some constant times the Dirac delta at that particular point, right? So this is nothing but delta at A1. So this will, what this implies? This implies that this is nothing but x minus A2 times x minus AN times t is nothing but C1 times delta A1, right? So next, but now we try to replicate the same process. Now we take S to be what? And now as you can guys can guess, this is nothing but x minus A3 times x minus an t, which is again a distribution. So we have what we x minus a2 s2 nothing but c1 times some Dirac delta a1, right? And what is it? This is what we have solved earlier again. So this was nothing but we have to this S2 is can be written as in general form the homogeneous plus the particular solution. And the homogeneous, we know what is the form of the homogeneous. This is some C2 times delta A2. And the particular solution is nothing but is nothing but given by this some C1 times so let me write first. And S2 is given by, first of all, we have to write the homogeneous solution, which is nothing but C2 times delta A2. This is my homogeneous part. Plus now we have to write the particular solution, and the particular solution is nothing but given by C1 delta A1 and then whole divided by A1 minus A2. Right? Because at the end I have to put A1 here and then ultimately I get the desired constant. So that is the thing. So this is the particular solution. Now what was C2? This actually implies that x minus A3 up to x minus an times t is nothing but C2 delta A2 and C1 delta A1 whole divided by A1 minus A2. Actually, the whole constant again can be another constant, C1 dash or something, but we will do that at the end. So now we actually now repeat the process. This will give x minus A4 times x minus an. T is nothing but some C3 delta A3 plus C2 delta A2. Now we have to divide by A3, A2 minus A3. And same goes with the remaining one. So C1 delta A1, A1 minus A2, and A1 minus A3. Continuing in this way, finally, we get what? We get what? T of this particular form, summation k1 to n, dk, delta ak, with dk of what form? Dk of what form? Dk can be given by dk, and we have seen this, that was ak minus ak plus 1, like the lower terms basically, ak minus an, and that we actually have to do for up to n minus 1, and dn is nothing but cn only, because we have seen that the last particular thing we get was the only single constant. So that's the distribution we have. Actually, we can remove these constants, and ultimately we see that T is nothing but Dirac delta only. Some some uh some constant, some linear combination of the Dirac deltas or those points where I'm basically multiplying the factor x minus ak. So that is the solution. So it's like uh, it has to be the case only, right? Because it's like it's if you see any function, so it's x minus a times f is 0 for all, let's say x. That will imply f is 0 at any point apart from a. But at a, we cannot say anything about that. But in terms of distributions, what we can say it has to be, it can actually say that the distribution, if it is a distribution, that at that particular point, it has to be a constant multiple of the drag delta of that particular point. Okay, so moving on. Next, we would like to see some question based on the convergence, the distribution spaces. So we'll have some questions on that. So let's have some questions based on that the convergence in. So before I write question, let me state, like, if I Tn is a sequence of distributions in this, then we say that Tn converges to T for some T in D if and only if Tn phi converges to T phi. So what is Tn phi? Tn phi now turns out to be a real number only. So we have this convergence in R only. In fact, we can have distributions on C complex numbers, but we will not go into that. We will just stick to the real number only. So we see that this is a particular convergence in the distributions, in the space of distributions. So this is nothing but actually, in some sense, it's a weak star convergence. Like if you guys know about weak and weak star convergence, so this is nothing but a weak star convergence. So that was fun, that particular notion. So let's have some questions based on it. So question number two. So as we know that any function, any L log function can give rise to a distribution. So we have proved that Tn equals to sin nx converges to 0 in the space of distributions. So this Tn sin nx is nothing but the distribution generated by sin and nx. And how do we basically write this thing? So let me write again. So Tn phi is nothing but the integral over R of sin nx times phi x t. So that's how you basically define the image of phi when a distribution generated by a function. So let us prove that this particular thing if converges to t, I have to show that this particular integral is converging to 0. Need to show in R in R only. So we have to see this particular integral. So now as phi belongs to what? Phi belongs to distributions. Then support of phi will be contained in, let's say, some minus a to a or some a positive, right? Okay, so what do we have now? Tn5 is nothing but this integral from minus a to a and sin nx phi x dx. So what now we try to do, we actually will use an integration by parts. So this is nothing but minus of integral minus a to a cos nx. So basically I'm taking the derivative to phi. So I'm integrating sine. So the integration of sine is actually minus cos nx whole divided by n into phi dash x dx, and all of this plus the boundary terms. But since the support of phi is inside minus a to a, so phi at a and minus a will be 0 only. So that boundary terms will not come. So this is nothing but minus a to a cos nx by n phi dash x dx. This the modulus of t n phi is nothing but less than equal to 1 by n. So modulus of cos nx is bounded by 1 only. And since pi is infinity, I can take their infinity norm out of it. And that is actually finite. And the measure of minus a to a, so this is nothing but 2a only. And what do we now see? This whole thing is bounded and a constant only. What this implies, this actually whole thing will converge to 0 because 1 by n tends to 0 as n tends to infinity. Thus, this will imply that t n phi has to go to 0 as n tends to infinity. And since that is the case, this implies that Tn actually converges to, since this holds any phi, Tn converges to 0 in distributional sense. Okay, so that's not a hard problem as long as you know the definition. So this wasn't that much hard. We'll have some more questions and let us try to like level up a bit, level up the questions a bit. So next, let us see the convergence of one more sequence. Next, again prove that I'm defining Tn as now sine nx whole divided by x. So now we have a division by x. Where this converges to? This converges to y to pi delta in dash. So how do we actually solve this? We will try to somehow convert this problem to a first problem and something else, something more, and then use that to eventually get this. So so let if I take phi to be some C infinity function, and T and phi is nothing but integral r sin nx whole divided by x to phi x dx. And now this can be written as minus a to capital A. As we have just seen this, we can write this thing for some A positive. Now next what we'd like to do, we have seen this again, we have a x in the denominator, and how we deal with this deal with x in the denominator, we need somehow a 0 phi in this somehow we need a 0 phi uh, so that we could eliminate this x in the denominator. So how we do that? We actually do like in this manner. We have done this in the last tutorial as well to eliminate this type of thing. This is sin nx, and then we were to do phi x minus phi 0 or divide by x, and then we add and subtract phi 0. This is minus a to a sin nx phi 0 or divide by x dx. Okay, so now we evaluate these both integrals separately. Now since phi c1, I can basically write my that phi x can be written as nothing but phi x equals to phi 0 plus x into psi x, with psi belonging to C0R. So basically I1 is now nothing but minus a to a sin nx and psi x dx. So actually we can take this to be C2 for a more better purpose, so that we can. So now this will imply that psi will be of space. Basically, I'll then phi is C infinity, so I can take it to C2 as well. Actually, this will give my psi to be psi1. And now we can use our previous part from previous question. We have, what do we have? We have the limit as n tending to infinity. I1 is nothing but 0 only, because now we can again use the integration by parts only. And once the integration by parts we can use, we can again, we have the this whole integral going towards 0 only. So next, so the I1 goes to 0. Next, we'd like to see what happens with the I2. So let us write I2. I2 is nothing but minus A2A sin nx phi 0x dx. So this is my A2, I2 phi 0 minus A2A sin nx whole divided by x dx. So let us get rid of n first from the sine part. So let nx equal to y only. This will imply n dx equal to dy. So I2 will be nothing but phi 0 minus, and the limits will be now this time will be minus na times na, and this is nothing but sine y. Means x will be y by n, but then n dx will be dy only. So this is y times dy. So the limit as n tends to infinity I2 is nothing but phi 0 and the integral over r of sine y whole divided by y dy. Now what exactly is this integral? This integral is nothing but this Dirichlet integral, and this is a quite famous integral. And the value of this integral is no is actually pi only. So this is nothing but phi 0 times pi, but that can be written as pi times delta at pi. So delta is the Dirac delta at 0. So what we actually end up, we end up getting the t and phi, the limit of t and phi. Is nothing but pi times delta phi. So what this implies that Tn actually converges nothing but pi times delta only. Okay, so that's how you prove, and we just check that this integral is very famous and can be evaluated the value to be pi only. So moving on, let's have more examples on this convergence of distributions. So we have question number 4. Uh, so for lambda positive, let t lambda, where this is actually distribution only, be defined by t lambda phi is integral minus pi by 2 to pi by 2 of cos lambda x divided by x into pi x minus pi 0 dx, and that holds for all phi in dr. So what now do we have to do? We have to basically find first limit lambda tending to infinity of t lambda, and the second thing which we would like to do is to again find the limit of lambda tending to 0 from the positive side of t lambda in d dash r. So these are the two limits which I would like to find. Okay, so how do we go about that? Let's proceed. So what do we need to find the limit as lambda tend to infinity? T lambda. What is T lambda phi? T lambda phi is nothing but minus pi by 2 cos lambda x pi x minus pi 0 x. So this whole thing can be written as minus pi by 2 to pi by 2 cos lambda x into psi x dx. Where again psi x is a function which is actually like if I take so if I so if I take so if I take basically phi to be C2, then psi is C1, and ultimately we can see as since we are tending lambda tending to go infinity, so this is more like the same problem where I can replace my lambda with an n, and this is again a sequence of distributions. So this actually again we can reduce much like the sin nx case that 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 whole this thing by integration by parts will actually be bounded and actually goes to zero. So you guys can check that. So by integration by parts, what do we have as limit lambda tending to infinity? T lambda phi is nothing but zero only. So next thing which you'd like to solve is limit as lambda tending to zero from the positive side d lambda in d dash r. So to find this limit in d dash r, again this time let us again type the integral version first. So d lambda phi is nothing but minus pi by 2 to pi by 2 cos lambda x psi x dx. Okay, so now first we look at the pointwise limit. So why is it that phi x is a continuous function, so it will be bounded in the region minus pi by 2 to pi by 2. Next, we would like to see that this cos lambda x actually converges to where only it converges to 1 as lambda tends to 0 from the positive hand side, and psi x will remain to be psi x only. And this whole thing mod cos lambda x psi x can be bounded over by mod of psi x and since this modulus is bounded by mod psi x only, and this is actually a since a continuous function, this is in L1 minus pi by 2 to pi by 2. So what do we have basically? Uh, we can basically apply the DCT since we have a pointless limit. So by DCT means dominated. Basically, we can now apply the dominant convergence theorem. We have limit lambda tending towards 0 minus pi by 2 to pi by 2 cos lambda x psi x dx to be nothing but minus pi by 2 to pi by 2 psi x dx. What this basically implied? This implied that limit lambda tending to 0 on the positive hand side, the pi is nothing but minus pi by 2 to pi by 2, and we can again write the value of psi x, which was nothing but phi x minus phi 0 whole divided by x dx. So this is actually the limit which you like to find. So the next thing which we are interested in is another sequence of distributions. This was question number 4. So what is the lim motion for any epsilon positive? Let f epsilon be defined by f epsilon x equal to epsilon by 2 mod x is to power of epsilon minus 1 for all x in R. Then what do we have to show? Then show that limit as epsilon tending to 0 from the positive hand side, f epsilon is nothing but Dirac delta in T dash R. So we just need to show that these are all distributions and the limit is actually this only. So clearly if epsilon r is a distribution, for any epsilon positive as mod x epsilon minus 1 is actually isn't actually L1 log of R. So this is locally integrable. So since again we have to see this in distribution sense, we will apply a phi only. So f epsilon at phi is nothing but the integral over R of epsilon mod x epsilon minus 1 phi x dx. So again this can be written as minus a to a. For some a positive. Again, this is possible in psi as complex support. So next would be, since we have a modulus of x here, we would like to divide this integral in two parts. Oh, there was a epsilon by 2 there. So let me put 2 here. Epsilon by 2 minus a to 0. And here we have minus x raised to power of epsilon minus 1 pi x dx. And this is nothing but 0 to a x epsilon minus 1 x dx. So now we change the variable in the first integration to get that epsilon by 2, and we'll take minus x equal to y, and again that change the main variable y to x only. This is not nothing but y epsilon minus 1. So well, we can change this to x only. 5 minus x dx, and that actually will be 0. It will be a to 0, and then minus will be there, and then it will ultimately end up with 0 to a only. X epsilon minus 1 phi x dx. So this is nothing but epsilon by 2, 0 to a, epsilon minus 1 phi x plus phi of minus x dx. So now basically what we have here is this phi x plus phi of minus x. So this actually now we can modify this particular thing. So we know that phi x actually can be written as phi 0 plus x times some psi x. And then again phi of minus x can be written as phi 0. This time we have a minus x psi of minus x. And moreover, supremum of mod x less than equal to a. So again, this is a support in A only. Less than equal to some actually constant times supremum of mod x a phi dash x. Actually, this comes from the actually mean value theorem only. So what this actually imply, if I add these two things, I get phi x plus phi of minus x to be twice of phi 0 plus x times phi x minus phi of minus x. So why we have done this? Because at the end, somehow I want to get an extra x in the equation. So this that's why we actually end up doing this only. So what this will imply? This will imply this f epsilon at phi is nothing but epsilon times phi 0 to a. So x raised to power of epsilon minus 1 dx. And then next is epsilon by 2, 0 to a. So next is x raised to power epsilon only. And this is nothing but phi x minus phi of psi of minus x. So again, we distribute this into integrals. This is I1 and this is I2. So what is I1? I1 is just by direct computation. We have nothing but a raised to power of epsilon divided by epsilon. And this thing actually tends to, so this thing only. And next we have I2. I2 is nothing but so we now use this bound of psi x, which is nothing but the supremum of phi dash. So this I2 is actually bounded above by phi dash xm. So ultimately this is nothing but 0 to a x epsilon dx into twice of some constant into the L infinity norm of phi dash. And that whole thing is 2c phi dash into L infinity. And this is a epsilon plus 1 whole divided by epsilon plus 1. Just basically this implies this I2 times epsilon, the whole bound. This thing is nothing but bounded above by 2c phi dash L infinity a epsilon plus 1 whole divided by epsilon plus 1 times epsilon. And this thing actually, this thing is bounded. This thing actually is again bounded and actually converges to 1. So converges to a only as epsilon tends to 0. And this tends to 0 as epsilon tends to 0. So what this basically implies? This implies this whole thing I2 times epsilon tends to 0 as epsilon tends to 0. So what this basically implies that this my f epsilon phi limit as epsilon tending to 0, f epsilon phi is nothing but the I1 is a raised to epsilon. So this is epsilon phi 0, a epsilon whole divided by epsilon, and then we have to take the limit epsilon tending to 0, and the next limit is 0 only. This is nothing but phi 0 only because a raised to epsilon when epsilon tending to 0 is nothing but 1 only. What is this? What is this? This is nothing but Dirac delta at phi only. So the main idea for this also this boundaries we are getting from the mean value theorem. The main idea was to write this phi x and phi of minus x with sum to be in the form of psi and minus psi, and that bound actually we can get in terms of phi dash only. Okay, so finally we see one more question, and what we basically see, even though we have pointwise convergence almost everywhere, that does not imply uh, distributional convergence at all. So not at all. Sometimes it may not imply. So based on that, we have one question. So let Fn be a sequence of functions on R defined by Fn x equal to n square 0 for mod x less than 1 by n, and this is for mod x greater than or equal to 1 by. Then what do we have to do? We have to show that Fn x, this whole thing, converges to 0 in R for x non-zero, but Fn, so we have a point-wise convergence, but Fn does not converges in D dash R. So the solution is, so clearly one thing which we can see here is that for any non-zero x, there exist some n not belong to n such that 1 by n naught is less than mod x. So when that the case, what this imply that f of m at x will be 0 for all m greater than or equal to n naught. And what basically this implies that fm x actually converges to, or that is fn x converges to 0 as n tending to infinity. So we have the pointwise convergence. Next, we would like to see this integral does not converge in distributional sense. So now consider f and phi, and is nothing but, what is this? This is nothing but integral of over R of fn x into phi x dx, which is nothing but this is 0 from outside the mod x less than n, 1 by n, and so this is nothing but minus 1 by n to 1 by n square phi x dx. So if this thing converges to something, let's say some number, so it has to happen for all phi. But if I take in particular, if we take phi x equal to 1, 1 minus 1 to 1, and phi is again a distribution. So this we can choose from the theory. Then Fn phi will be nothing but n square times 1 by n minus 1 by n. So this is nothing but 2n. And this thing actually tending toward infinity as n tends to infinity. So this actual thing doesn't converges to any point. So that's we have here. So that actually since this doesn't convergence for this particular phi, this implies Fn doesn't converge in d dash r. So that was the case. But next we have one more question which actually says that where we have a again we have a pointwise convergence, but again at the same time this time we have a convergence in distributional sense. So it's one example where at least we have distribution convergence. So that is not the case if we have a pointwise convergence that not imply the distributional convergence. So this is question number 7. So let Gn be a sequence defined by n by 2 0 for mod x less than 1 by n, and this is for mod x greater than 1 by n for all n in n. So what do now we have to show that first part that g and x, this converges to 0 for x non-zero, and the second thing which we like to show is that this gn, this converges this time in distribution sense to Dirac delta in d dash r. So now to prove this, first of all, again we have this same thing as we have earlier in the pointer sense, that for any again non-zero x, there exists some natural number n naught such that 1 by n naught is less than mod x, then gmx is 0 for all m greater than equal to n naught. Right, because that's the definition, because it's only non-zero inside minus 1 to n, minus 1 by n to 1 by n. Thus, this gnx converges to 0 as n tends to infinity. So next we show that this thing actually converges in distributional sense. If I consider gn phi, what is this? This is nothing but minus 1 by n to 1 by n gnx. Actually gnx is nothing but n by 2 here only, n by 2 phi x dx. Okay, so now we have to show that this actually converges to phi 0 only. So what we can do here is either we can have phi x minus phi 0, but what we can do here is we can use the mean value theorem for integrals to get for something n by 2 phi xi n times the measure, which is 1 by n minus 4 some xi n belonging to minus 1 by n to 1 by n. So this is the mean value theorem for integrals. So what is it? This is nothing but half. This is nothing but phi xi n only. And as n tends to infinity, the xi n is lying in between minus 1 by n only. So xi n has to go to 0 only. But this basically now, but I know that phi is continuous, but this implies that phi of xi n will converges to phi of 0 only. Then what this implies that gn phi, this limit as n tends to infinity is nothing but phi o, which is nothing but Dirac delta at O. So what this basically implies that gn actually converges to Dirac delta in distributional sense. Right, so I hope that actually clears the idea of this convergence in the distributional sense. And I hope that clears a lot of ideas in the distributions. Next, this since these things are actually not so hard. You just have to apply the definitions and all, and things are actually work out. You just have a good command in integration, and not even that. Basically, you just have some manipulations, and you see whether there's a singularity in the denominator or not. If yes, then you have to see how to tackle that particular singularity. The main idea is since phi is a CZ infinity functions, you can like extract out, you can apply the Taylor theorem and all ultimately to get some so you can reduce the integral into a more more a better integral in a more uh, in an integral which can be solved in a more easier way. So that's all I would like to say for this convergence in the distributions. And uh, with that, I hope the ideas are clear and you have may have more insights in how to see the convergence of distributions into convergence sequence in the space of distributions. And yeah, I guess with that, I would like to end the today's session. Thank you. We'll meet next week.